The experimental method to conduct heat transfer measurements is called calorimetry. And there are two procedures to conduct calorimetric measurements. The first one is called the constant volume calorimetry, or the bomb calorimetry, where you actually do the experiment in a sealed container that does not allow the sample to expand or compress. So it has a constant volume. As we know, the change in internal energy for the system is going to equal the heat transfer minus P delta V, but this is conducted under constant volume, so no expansion or compression is allowed. So this term is going to be zero. And whatever heat transfer will take place in the experiment is going to equal directly the change in internal energy for the system. Whatever heat is produced from the reaction is going to equal the sum of heat gained by the surrounding water and the bomb itself. And of course, you can calculate both of these quantities using the famous formula Q equals mc delta T for water, and Q for the bomb is going to equal the heat capacity for the bomb times the change in temperature. Let's go over one example of such a measurement here. So in this example right here, you're burning this compound in a constant volume bomb. So in this case, the container or the bomb temperature rose from an initial temperature of this value to a final temperature of this value. And it gives you here the heat capacity of the whole thing, including water and the bomb itself. And it asks to calculate the molar heat of combustion. In this case, since this is a measurement under constant volume, so what we're calculating here is actually the change in internal energy for the reaction. Based on the first law of thermodynamics, whatever heat produced from the reaction is gonna be completely gained by the calorimeter, of course, under constant volume. And we can calculate the amount of heat gained by the calorimeter using the formula Q equals C delta T, the heat capacity times the change in temperature. So it's gonna equal 10.17 kilojoules per degree times the final temperature is 25.95 degrees minus the initial temperature 20.28 degrees. This is going to give you 57.66 kilojoules. And here from this equation, Q of the reaction is going to be negative Q of the calorimeter, so it's going to equal negative 57.66 kilojoules. But this amount of heat was produced from that mass of the sample, and here it asks to calculate it per mole, or to measure it per mole. So what we want to measure is actually delta E of the reaction per mole. So this is going to equal the heat of the reaction divided by the number of moles in the sample. So it's going to equal negative 57.66 kilojoules divided by the mass, 1.435 grams. And then we need to convert number of grams to number of moles using the molar mass, which is 128.2 grams per 1 mole. And that should give you the molar heat of the reaction, or the molar change in internal energy for the reaction. And it should equal negative 5.151 times 10 to the power 3 kilojoules per mole. Again, that value here is the internal energy change for the reaction, because it's measured under constant volume, as the problem said. The Second way to conduct calorimetric measurements is doing the measurement under constant pressure. And if you're doing the measurement under constant pressure, the sample can compress or expand, which means there is a possibility for work to take place. We know that the change in internal energy equals heat transfer plus work, but work equals negative P delta V. So the change in internal energy equals the heat transfer during the experiment minus P delta V. So the heat transfer that you will experimentally measure is going to be the sum of the change in internal energy plus P delta V product. So that term here is a different value than the change in internal energy alone. It's going to be a different amount of heat transfer that you will measure in this case. And that amount of heat transfer, which is the sum of the change in internal energy plus P delta V, is going to be a new property, which is a change in enthalpy for the system. So the heat transfer that you measure at constant pressure is not going to equal the change in internal energy. It's going to equal the change in internal energy plus the expansion compression work, which is the change in enthalpy for the system. So that introduces a new property for any system, which is enthalpy, which is another state function for the system. So being a state function means that the change in this property is going to be simply the difference between the final state of the system minus the initial state of the system. Whenever you do a calorimetric measurement under constant pressure, you're actually measuring heat transfer that equals the sum of change in internal energy plus the expansion work, or it equals delta H of the reaction or the change in enthalpy of the reaction. It's not measuring the change in internal energy. It's measuring the change in enthalpy for the reaction. And you do the measurement in the same way. You can actually calculate the heat of the reaction under constant pressure from the heat gained by the calorimeter, and you can calculate the amount of heat gained by the calorimeter using MC delta T and heat capacity times change in temperature for the calorimeter based on the first law of thermodynamics. If you are reacting a solution of HCl with a solution of NaOH in a calorimeter of negligible heat capacity, the initial temperature of the solutions increased from 22.5 to a final temperature of 25.86, and it wants you to calculate the heat change for the reaction per mole. Since this is done under constant pressure, what you're actually calculating here is going to be the change in enthalpy for the reaction, delta H for the reaction. The heat produced from the reaction is going to be completely transferred to the calorimeter. But it said here that the calorimeter has negligible heat capacity, so all the heat produced from the reaction is going to be completely transferred to the solution itself of the reaction, the water of the solution of the reaction. And we can calculate the heat gained by the water of the reaction from the formula MC delta T. So we start with the volume of the solutions that we mixed. We have 100 mils here, 100 mils here, so we have a total volume of 200 milliliters. And then we assume that this is mainly water, so we can use the density of water to convert volume to mass. 1 gram of water is 1 milliliter. So this conversion factor converts the volume to mass, and then we multiply times the specific heat capacity for water, 4.184 joule per gram per degree, times the change in temperature, which is the final temperature, 25.86, minus the initial temperature, which is 22.5 degrees, is going to give us an amount of heat gained by the solution that equals 2.81 times 10 to the power 3 joules, or 2.81 kilojoules. So, and from the equation here, Q of the reaction is gonna equal negative Q of the solution. So it equals negative 2.81 kilojoules. But this amount of heat was produced from a specific sample with a certain number of moles. If you want to calculate it per 1 mole, you calculate delta H of the reaction by dividing the heat of the reaction during the experiment by the number of moles of the reaction. So it's going to equal negative 2.81 kilojoules divided by the number of moles of the reaction, which can be calculated from the molarity of the reaction, mole per liter, times the volume of the reaction in liters, 0.1 liters, right? And you calculate this, it gives you the molar heat of the reaction, and it's gonna equal negative 56.2 kilojoules per mole. Just to differentiate between the two properties, enthalpy versus internal energy, or the two types of measurements that we conduct in calorimetry, measurement under constant volume versus measurement under constant pressure. This example here is gonna be very helpful. If you conduct this reaction under constant pressure, it's gonna actually release an amount of heat that equals this value here. And this is gonna be the amount of the change in enthalpy for the reaction. What about the change in internal energy? If you measure the same reaction under constant volume, is going to give you a different value for the heat transfer, which is going to equal the change in internal energy. But we can still calculate the change in internal energy for this reaction from the constant pressure measurement. Because as we know, the change in internal energy equals the change in enthalpy minus P delta V. We have the change in enthalpy, we have the external pressure, but we don't have the change in volume. But these are all gases, so we can actually use the ideal gas law, PV equals nRT. So we can actually calculate the change in volume from the change in number of moles during the reaction, right? And the change in number of moles is going to equal the final number of moles of the reaction minus the initial number of moles of the reaction. So it's going to equal 2 moles minus 1 plus 2, 3 moles. So it's going to be minus 1. And we can just substitute for these numbers in the equation. So it's going to equal negative 566 kilojoules per mole minus the change in number of moles times R times the temperature in Kelvin. But this term here is going to give us energy in joules, but the energy here is in kilojoules, so we have to convert to kilojoules, and we conduct the calculation. Is going to give us negative 563.5 kilojoules per mole. This is the change in internal energy, and it's actually the same as the heat transfer that you would have obtained if you conducted the experiment under constant volume, right? And the difference between the two values, negative 566 kilojoules and negative 563.5 kilojoules is actually equal to the expansion compression work. So the difference between the change in internal energy and the change in enthalpy for any reaction is the expansion compression work of this reaction. Just to again emphasize the differentiation between the two properties, internal energy is the sum of all types of energy that is used to create the system. Electronic energy, kinetic energy of the electrons and nuclei, the bonding energies, and so on. And when you change the energy of the system to a different value or a different state, the change in energy or in internal energy for the system in this case is going to equal the heat transfer under constant volume. So if you do the reaction or the measurement under constant volume, you will be directly measuring the change in internal energy for the system. On the other hand, enthalpy is the total energy in the system plus the expansion compression work. So if you change the enthalpy of a system from one value to the other, the change in enthalpy is going to be the sum of the change in internal energy plus the expansion compression work, which is going to equal the heat transfer that is going to take place under constant pressure. And the difference between enthalpy change and internal energy change is going to be the expansion compression work. So just to emphasize, internal energy is the sum of all the types of energies used to create your system. Enthalpy is the total amount of energy in the system used to create the system plus the energy used to expand or compress the system. And in case of solids and liquids, the change in volume or the expansion or compression is very negligible, which makes a difference between internal energy change and enthalpy change negligible. However, in case of gases, this is going to be not negligible. You will have significant expansion and compression taking place during gas reactions, and the change in enthalpy for the reaction is going to be significantly higher than the change in internal energy. What we commonly measure during most of the reactions is change in enthalpy, because we actually do most of the reactions in open containers under constant pressure, right? So whatever heat is given off or absorbed during any process in this condition is going to be a direct measurement for the change in enthalpy of the process. But enthalpy is a state function, which means the change in enthalpy is going to be the difference between the absolute enthalpy of the reactants minus the absolute enthalpy of the products. So the difference between both of them is going to be delta H, because it's a state function. And in case of an exothermic process, you will be moving from higher energy reactants to lower energy products. So the change is going to be negative, right? In case of endothermic reactions, you will be moving from lower energy reactants to higher energy products. And this is why it needs to absorb energy, a positive change in enthalpy for the system. But we cannot measure the absolute enthalpy for any substance. This is impossible. We also don't have to measure the enthalpy change for every reaction that is of interest to us. What we will do is we will define the standard enthalpy of formation for any substance, which is going to be the heat change during the formation of 1 mole of the compound from its elements. And we will selectively make the heat of formation of any element in its most stable form to equal 0, and make this our reference for any other process. So O2 is the most stable form of oxygen, so it will have heat of formation that equals 0. Graphite is the most stable form of carbon, so it will have heat of formation that equals to 0. On the other hand, something like ozone is not a stable form of oxygen, so it's not gonna have a zero heat of formation. Diamond is also not the most thermodynamically stable form of carbon, so it will have a non-zero heat of formation. And as we said, we will make a scale of standard enthalpy change of any reaction, and we will make a selective reference point, 0 point, that corresponds to all types of elements in their most stable forms. We'll make those equal to 0, and then we will refer any other heat of formation for any other substance to their elements. So the heat of formation of a reactant is going to be the difference between its elements and the reactant itself. But since we made the elements equal to 0, so that is going to be an kind of an absolute value. And the same thing for any product is gonna be the difference between the elements, which are 0, to the heat of formation of the reactant itself. So if we want to measure the change of enthalpy for a reaction between a reactant and a product, is going to be the heat of formation of the product minus the heat of formation of the reactant. That makes our life significantly easier for these calculations. And this is basically Hess's law, is that the change in enthalpy for any reaction is the same whether you make it in one step or in several steps. That makes the change in enthalpy for the step changing these reactants to these products the same as if you take the reactants back to the pure elements and then combine the elements to make the products. So we have elements to be a reference point that equals 0. So that's why the change in enthalpy for this reaction is going to be simply the difference between the sum of heat of formation of the products times their number of moles minus the sum of the heat of formation of the reactants times their number of moles. So for example, if we are considering this reaction right here, you're moving from the reactants, let's name them A, to the products B in one step. And the heat of formation for this reaction, or the standard enthalpy change for this reaction, is going to be the same as if you take the reactants to the elements first. So going from glucose back to the elements themselves is the opposite of formation. So it's going to have an energy of negative of the same value, right? And taking oxygen to the pure form is again the opposite of formation. So it's negative delta H of formation for oxygen. And then you take these elements and combine them to make the products. So this is delta H of formation for carbon dioxide. And you take hydrogen with oxygen to make water. So this is delta H of formation of water. So the change in enthalpy for the reaction overall is the same as the overall change in enthalpy for all these steps right here, right? It's the same thing because you are moving from the same start point to the same end point. And since enthalpy is a state function, whether you take it in one step or in several steps is going to be the same difference in the property. So the delta H of the reaction right here is going to be the sum of all the heat of formation of the products times their number of moles in the equation minus the sum of all the heat of formation of the reactants times their number of moles in the equation, right? So let's do an example right here. For this substance, when you burn it in oxygen, it's going to make boron oxide and water. If you want to calculate the heat released per gram of the compound, using the standard heat formation of the substances involved in the reaction. As we said, heat of formation of the reaction is going to be simply the sum of number of moles times the heat of formation of all the products minus the sum of number of moles times heat of formation of all the reactants. So it's going to equal 5 times heat of formation of barium oxide, boron oxide, plus 9 times heat of formation of water. These are all the products, minus 2 times heat of formation of pentaborane, plus 12 times heat of formation of oxygen, right? This here is 0 because it's an element in its most pure form or most stable form. And then we will just put in the numbers for the other substances. So it's going to be 5 times negative 1263.6 kilojoules per mole, plus 9 times negative 285.8 kilojoules per mole, minus 2 times 73.2 kilojoules per mole. So that is gonna give us the heat of the reaction that is gonna equal negative 9036.6 kilojoules per mole. So in general, the change in enthalpy for any reaction, as we said, is the state function. So whether you take the reaction in one step or in several steps is going to be equal. So if you're reacting graphite with oxygen to make carbon dioxide in one step, it's going to release that amount of heat right here, which is going to equal to the sum of the heat released from the conversion of graphite to carbon monoxide, followed by the conversion of carbon monoxide to carbon dioxide. So it's as if you're actually adding the two reactions to each other to come up with the overall reaction. So the reaction from graphite plus oxygen to carbon dioxide is gonna be the sum of the two reactions from graphite to carbon monoxide followed by carbon monoxide to carbon dioxide. So that reaction here is gonna equal the sum of these two reactions, which will make the change in enthalpy for this reaction right here equals the sum of the change in enthalpy for reaction 1 plus of the change in enthalpy for reaction 2. So we can, whenever we're doing this type of calculation, we have to follow a couple of rules right here, is that we will have to take into account the stoichiometric coefficients in the reaction, because it's gonna refer to the number of moles of the substance. So that reaction here tells you that in order to melt 1 mole of ice into liquid, you would need 6.01 kilojoules of heat. The second rule is that if you reverse the direction of the process, you will have to reverse the sign of the change in enthalpy. So if you are going the other way around, freezing 1 mole of water into ice is gonna release the same amount of heat into the environment. So it's gonna have a negative sign to indicate that it's releasing the energy instead of absorbing it. The third rule is that if you multiply an equation times any factor, you will have to multiply the whole equation times the same factor. So if you multiply the conversion here times 2, you will have to multiply the amount of heat needed by 2 as well. And the last thing is that you have to pay attention to the physical states of the substances, because of course, different physical states is going to require different types of energies or different amounts of energies. If you produce water in the solid form, is going to have different energy than water in liquid form, with a difference of 6 kilojoules per mole. And if you produce it in the gaseous form, it's going to even have a more significant difference. Let's apply these rules to this example right here. If we consider this reaction between graphite and hydrogen to make acetylene, this is a very difficult reaction to measure experimentally. However, we can calculate the energy change or the enthalpy change during this reaction if we have information about this set of reactions right here, which are easy reactions to measure experimentally because they're combustion reactions. So you just burn the substances in oxygen, and you measure the heat change during each of these reactions. So what we need to do is rearrange these three reactions to come up with this reaction right here. So we need to have 2 moles of graphite on the left-hand side of the equation. So we need to multiply this times 2, because it's gonna, when you multiply it times 2, it's gonna make 2 moles of graphite plus 2 moles of oxygen. It's gonna give you 2 moles of carbon dioxide. And of course, you will have to multiply this times 2 as well. And then we have 1 mole of hydrogen. We need 1 mole of hydrogen in the left-hand side. We already have 1 mole of hydrogen, so we don't need to change this reaction. And we need 1 mole of acetylene on the right-hand side, which means we have to multiply this times -1 to reverse it. And we also have to multiply it times 1/2 to make the number of moles of acetylene 1 instead of 2. So it's going to be multiplying times -1/2. When you multiply the third reaction times -1/2, it's going to give you 2 moles of carbon dioxide plus 1 mole of water. Is going to give you 5/2 of oxygen plus 1 mole of acetylene, which is what you want on the right-hand side. And of course, you will have to multiply this times -1/2 as well. If you add up all of these reactions, it's going to cancel out 2 moles of carbon dioxide with 2 moles of carbon dioxide, 1 mole of water with 1 mole of water, 5/2 moles of oxygen with 2.5 moles of oxygen, and you will be left with 2 moles of graphite plus 1 mole of hydrogen. That gives you 1 mole of acetylene, which is the same reaction of interest right here, which makes change in enthalpy for this reaction equal 2 times delta H1 plus delta H2 plus -1/2 times reaction 3. So we simply add those up. Again, after you multiply this times 2, add it up to this, and plus -1/2 times this. And it's going to give you the enthalpy change for the reaction, which is going to be 226.6 kilojoules per mole. And in all of these thermodynamic calculations, you will have to, again, pay attention to the stoichiometry. It's going to be the same type of stoichiometric calculations, but now you just added 1 more component to the equation, which is energy. And whenever you do any calculations, you have to take the mole ratio of the balanced equation into account, right? So you have to always make sure that your equation is balanced before you do any calculations based on the stoichiometry of the equation. So in this example right here, when you react aluminum with iron oxide, it produces aluminum oxide and iron, and this is an extremely exothermic reaction to the extent that it actually produces enough heat to melt iron. And this is why it's typically used to weld metals together. So if you want to calculate the amount of heat released per gram of aluminum, you can calculate delta H of the reaction from the Hess formula, that it equals the sum of number of moles times delta H of formation of the products minus the sum of number of moles times delta H of formation of the reactants. So it's gonna equal delta H formation of aluminum oxide times 1 plus 2 times delta H of formation of iron in the liquid form minus reactants, so minus 2 times delta H of formation of aluminum in the solid form plus delta H of formation of iron oxide, right? This here is 0 because it's the most stable form of aluminum. It's solid metal. All the other substances here, we are using the standard heat of formation for each of them from the tables. For aluminum oxide, it equals negative 1669.8 kilojoules per mole plus 2 times 12.4 kilojoules per mole for liquid iron minus delta H formation of iron oxide is negative 822.2 kilojoules per mole, and that is going to give us a molar heat of the reaction that equals negative 822.8 kilojoules. But we're actually asking for the heat released per gram of aluminum. So the heat released per gram is going to equal the heat of the reaction divided by number of moles times the conversion factor between moles and grams, which is molar mass. So 1 mole of aluminum is 26.98 grams. So it's going to be negative 822.8 kilojoules divided by 2 moles of the substance, right? Times 1 mole divided by 26.98 grams, moles with moles, and it's going to give you the amount of heat in kilojoules per gram, and it's going to equal negative 15 kilojoules per gram. And as you can see, it's a huge amount of heat, and negative here to indicate that it's an exothermic reaction, which means it releases that much heat.